Hi, I'm Mr. Walker, and I'm going to go through the NZQA's Level 1 Science 2014 paper on acids and bases, so that's the chemistry paper. Now before we begin, you'll get the most out of this, I think, if you download the paper, print it off, have a go at yourself, and then watch through these videos as you check over your answers and add to them to make sure that you're getting a full and complete answer. So question 1. You're given the names of 3 compounds and you've got to use the table of ions to construct the symbol formulas, the correct symbol formula for these ionic compounds. So calcium chloride, you look at the table and you can see it's Ca2+, and chlorine is Cl-. So we'll write those ions down, and then we do the swap and drop. And so the value of 2 from the charge on the calcium ion goes down to the right hand side, bottom right hand side of chlorine, and the value of 1, since chlorine has a single negative charge, goes down to the right hand side of the calcium. And when we have a 1, we ignore it, and so we just write CaCl2 as calcium chloride. For sodium nitrate, it's a little bit more complex because we need to use brackets. So when we've got 2 or more elements in an ionic group, we're going to use brackets to make sure we don't confuse ourselves. So we write the ions again, sodium and then the nitrate taken from the table, and we put the bracket around the nitrate and we just leave the charge on the outside. We then swap and drop, and because it's 1 after each of them, we can remove the 1. And because the 1 is after the brackets, it's just one lot of whatever's in the brackets, we can eliminate the brackets as well, giving us sodium nitrate as NaNO3. And then zinc nitrate, again we write down the ion or ionic groups involved, bracket the nitrate, do the swap and drop, so the 2 will come outside the brackets this time. We can eliminate the 1 for the zinc, but this time because the nitrate is in brackets and it has a number after the brackets, we have to leave both the number outside the brackets and the brackets themselves, giving us Zn brackets NO3 close brackets 2. So we just write those in on the paper for the answers, and that's the first question done. So in question 1b, we need to give the electron arrangements of each of the atoms listed. We've got magnesium and aluminium to do because oxygen's been done for us. And I've left a little excerpt of the periodic table down at the bottom there for us to see where I'm getting some of this information from. So magnesium has an atomic number of 12. The electron arrangement, the first shell takes 2, leaving you with 10 to account for. And then the next shell would take a maximum of 8. So if we've lost 2 from 12, then another 8 from that value, we've got 2 left over, and so there's 2 in the final electron shell for a magnesium atom. We know that for an atom the electron arrangement is the number of electrons, is the same as the number of protons. So because the atomic number tells us the number of protons, and it's an atom, meaning it has no net charge, it must have the same number of negative charges as positive charges, so the same number of protons and electrons. So when magnesium forms an ion, it's going to get that stable outer shell, which in this case will be 2,8. One way to think about it is how easy is it for it to lose or gain electrons in order to fill its outer shell, and so it could either gain 6 or lose 2, so the magnesium atom will lose 2 to form the ion. So if it loses 2, then that leaves us with 2,8 as the arrangement of the ion. And then the charge on the ion, because the magnesium has 12 protons, but as an ion it only has a total of 10 electrons, then that means that it has 2 more protons, so 2 more positive charges that aren't accounted for by the negative charges, so it's a +2 charge, or 2+. On to aluminium. So we know the atomic number is 13. So as an atom, it's going to have 13 protons and 13 electrons. And so we need to fill the electron shells with those 13. First shell will have 2. The next one will have 8. That's accounted for 10 of the electrons, leaving us with 3 in the third shell. And then for the ion, it's going to again get that stable full outer shell. And so the way that aluminium will do that is by losing 3 electrons, giving it the same electron arrangement as the magnesium and oxygen ions. And the charge on the ion, because it's lost 3 electrons, that means it now has 3 more protons, positive charges, than it does negative charges, and so it's going to be 3 plus. So this question is going to require a little bit more writing. We're given 2 ionic formula, magnesium oxide and aluminium oxide, and we've got to discuss why the 2 formula are different. And the key word there is explain. That keyword's telling you that there's going to be a little bit more detail needed in your answer, and you are going to have to give an explanation as to why those 2 formula are different. And if you treat each bullet point as a to-do list, as an item on your to-do list, then you should, by the end of it, have done a pretty good job of everything that the question asks of you. So first thing, I'm looking at what the ions, the charges on the ions that are involved. And so I've stated that the magnesium will have a charge of 2 plus, aluminium ions will have 3 plus, and oxygen ions will have a charge of 2 minus. That's just taken from the previous question, the answer that we gave. So what does this mean? Well, it means that each of those ions loses or gains a certain number of electrons in order to form the ion. And because magnesium loses 2 electrons but oxygen would gain 2, they would bond in a 1-to-1 ratio, because the magnesium, the 2 electrons that have been lost, would be gained by the oxygen ion, would be gained by the oxygen atom to form the ion. And so that's a perfect 1-to-1 ratio. So 1 magnesium to 1 oxygen, hence the formula is MgO. And I've stated there that the ionic compounds have an overall neutral charge due to the loss and gain of an equal number of electrons. So if we compare that to the formula for aluminium oxide, the aluminium is going to lose 3 electrons when it becomes an ion. The oxygen will gain 2 electrons. Now those numbers don't balance up, so the simplest ratio that's going to account for that is to have 2 aluminiums losing a total of 6 electrons, and therefore 3 oxygens that will gain a total of 6 electrons. And that gives us the ratio of 2 aluminium ions to 3 oxygen ions. And so the formula is Al2O3. So on to question 2, and the more practice papers that you do, the more you'll recognize the type of questions that are asked. Very often it's extremely similar questions. There's only a limited number of questions that you can be asked in the NCEA papers. So if you've done a few years of past papers, then you'd certainly be able to start to spot those patterns, and you'd feel very comfortable about how you're going to answer the questions. So this question is all about rate of reaction, and it's starting off with a nice simple one about why the balloon inflates. So the balloon inflates because we've got calcium carbonate and hydrochloric acid, and you should know the general formula for a metal carbonate plus acid reaction, and the 3 products would be a salt, water, and carbon dioxide. So what makes the balloon inflate is the product carbon dioxide, it's released as a gas from the reaction. And because the gas occupies a much larger volume when it's released as carbon dioxide than when that carbon and oxygen was bound in the carbonate, then the gas bubbles as they escape expand in volume and fill the balloon. So now we come to the real crux of the question, a bit about the rate of reaction. Why does the balloon inflate faster when powdered calcium carbonate is used? So using the powdered calcium carbonate decreases particle size and increases the available surface area of the calcium carbonate that can react with the hydrochloric acid. And so because the rate at which carbon dioxide is released is determined ultimately by the rate of reaction, powdered calcium carbonate with a smaller particle size and greater surface area will increase the number of successful collisions per unit time between the hydrochloric acid and calcium carbonate. So more products created in a shorter time. And in that way, the carbon dioxide gas, because it's released more rapidly, will cause the balloon to inflate faster. It's important to relate anything to do with rate of reaction to the number of successful collisions in a space of time, or the frequency of successful collisions. And a successful collision is a collision between two reactants that has the correct orientation and the correct energy in order for a change to take place. So decreasing the particle size is one way of increasing the rate of reaction. There are alternatives, and here we've got to describe or discuss a different way that we could use to make the balloon inflate more rapidly. So here's some options. You could discuss an increase in temperature. You could talk about the use of a catalyst. You could increase the concentration of one or both reactants, or you could agitate or shake or disturb the flask as the reactions are going on. And so I think I've picked two of them to talk about. Increasing the concentration, in this case of hydrochloric acid, would mean that you've got more particles of the acid in the same volume, and that would lead to more successful collisions between the reactants in the same space of time, increasing the rate of reaction and creating the product, all of the products more rapidly, but we're really interested in the carbon dioxide because that's what makes the balloon inflate faster. Alternatively, we could increase the temperature at which the experiment occurs, and the particles would therefore have more kinetic energy. So if the particles have more kinetic energy, what we're saying is that they're moving faster. And if they're moving faster, then when they collide, they have more energy, and there's more likely to be a successful collision between the reactants. And that would also create a higher rate of reaction. So more carbon dioxide produced in the same time, and leading to the balloon inflating faster. So you'll undoubtedly have to write word equations and balanced symbol equations in your chemistry paper. This represents a really easy way to make sure that you're getting some points towards merit or excellence. The word equation is normally achieved level, the correct symbol equation is normally merit level, and a correctly balanced symbol equation would contribute towards excellence. So it's very worthwhile making sure you've got this skill so you can complete it in an exam. Alright, so the word equation for calcium carbonate and hydrochloric acid, well, it's a metal carbonate plus an acid, and so you know that the three products are going to be a salt, carbon dioxide, and water. The salt will take its name from the calcium, and hydrochloric acid always produces a chloride in the salt, so it becomes calcium chloride. So the word equation is calcium carbonate plus hydrochloric acid, and then we draw an arrow rather than an equal sign. So an arrow towards calcium chloride, carbon dioxide, and water. It doesn't matter which way round the reactants are and which way round the products are, as long as the reactants are to the left of the arrow and the products are to the right hand side of the arrow. So I could have written as the products water plus calcium chloride plus carbon dioxide. The order doesn't matter. Okay, so the formula for calcium carbonate, CaCO3, and I'll show you how we get that. Calcium carbonate, write down the ions, so with the carbonate group and the calcium, put the brackets around the carbonate, swap and drop. The numbers 2 to 2 represent the ratio, and because it's the same ratio as 1 to 1, we can simplify it down, giving us CaCO3. And because we simplified down the 2's to 1's, that means we can remove the brackets because we ignore any 1's outside of the brackets. Calcium chloride, I think we've done this one before. Calcium, chlorine, swap and drop, get rid of the 1, CaCl2. Okay, so the next thing we've got to do, if we're happy with all of the formulas there, hydrochloric acid is just worth pointing out. I'd expect you to memorize the formulas for hydrochloric acid, nitric acid, and sulfuric acid. You can work them out, but those three are pretty easy to memorize, and you'll guarantee to see at least one of them in your exam. Okay, so on to balancing the equation. So I would start from the left-hand side, and I would count the number of each atom or element that appears in the formula. And so calcium, I've got 1 on the left-hand side of the arrow. On the right-hand side, I've got another calcium. So that's 1 and 1. I'm happy with that. Carbon, I've got 1 on the left. Just watch out because there's other capital C's there, but they all represent something else. And then I've got 1 carbon on the right-hand side. I've got 3 oxygens on the left, and I've got 2 plus 1 is 3 on the right. So that's all good. Hydrogens, I've got 1 on the left, and I've got 2 on the right. So I need to get another hydrogen on the left-hand side. And chlorines, I've got 1 on the left and 2 on the right. And so what that means is I need another hydrogen, another chlorine on the reactant side. And so that's nice and easy to do simply by adding another molecule of hydrogen chloride of the hydrochloric acid. So I can write a big 2 in front of the HCl, and that is now a balanced symbol equation. All right, on to question 3. So we're in part A, we're going to identify what each of these liquids are based on the information that we're given in the table. So I'll go through this bit fairly quickly because the explanation comes in part B. So beaker 1 stays blue in blue litmus, stays red in red litmus, and it's green in universal indicator. All of that's telling me it's neutral, and so if I'm choosing from water, solution of baking soda and vinegar, then I know that the first one, beaker 1, is going to be water. Beaker 2, it turns blue litmus paper red, so that tells me that I'm dealing with an acid. There's only one acid there, the ethanoic acid, that's the white vinegar, so beaker 2 must be the ethanoic acid. And beaker 3, by default, then must be the sodium hydrogen carbonate. But if I look at the color of red litmus, the fact that the red litmus paper has turned blue tells me that I must be dealing with a base or alkali, and so I know that that's the sodium hydrogen carbonate. Okay, so I've put the table in with our answers from part A down at the bottom, so you can refer back to that. And we've got to use the information to show how we identified each of the liquids. Okay, we want to use all of our observations for each beaker. Remember, I would treat these bullet points as a tick list, and as you've done them, tick them off, and that makes sure you've got a full and complete answer. And then we're going to state the approximate pH from the color of the universal indicator. Alright, so beaker 1, it doesn't change either of the litmus papers. That tells us that the solution is neutral, so it's got a pH of 7. The fact that with universal indicator it turns green just reinforces that. Again, green result with universal indicator is neutral, or pH 7. And so of the 3 options, only water would have the neutral pH. Beaker 2, blue litmus paper turns red, red litmus paper stays red, so that's telling us it's an acid. And the universal indicator orange tells us that it's a pH less than 7, probably around 4 to 5. So this one must be the ethanoic acid. And beaker 3, blue litmus stays blue, red litmus turns blue. That tells us that it's an alkali or base, and universal indicator turns blue. So again, that just reinforces this idea. A blue color with universal indicator would suggest a pH probably between about 8 and 11, and that must therefore be the sodium hydrogen carbonate. And so as that's in solution, that's an alkaline solution. So on to question 3C, and this is a classic question in the science exam, the acids and bases exam, where you've got to relate the pH of solutions to the ions that are contained. So we're told that beaker 4 has a pH of 1, beaker 5 has a pH of 6. They're both acidic then, because they're both lower than 7 on the pH scale, we know they're both acidic. And that means straight away that they must have a higher ratio of hydrogen ions than hydroxide ions. So a lower number indicates a more acidic substance. Because beaker 4 has a lower pH, then that is the more acidic substance. So we've ticked off the first bullet point. And just to reinforce that, I'm going to say that pH of 6 is closer to neutral and is therefore less acidic. So beaker 5 is less acidic. Alright, so to compare the amount of hydrogen ions and hydroxide ions, beaker 4, because it's more acidic, it must have a much higher ratio of hydrogen ions than hydroxide ions. And this might be easier to see in a diagram as I explain it. So there's a little picture. We can see there's a lot of hydrogen ions and only a couple of hydroxide ions. Now, we're never going to be talking numbers that small, really, but that's just a representation of the ratio that might be found in that solution. By comparison, beaker 5, it still contains more hydrogen ions, but the ratio of hydrogen to hydroxide ions is lower. So there's more hydrogen ions than hydroxide ions. And you can see that in the diagram here. We've got 1, 2, 3, 4, 5, 6 hydrogen ions, but 4 hydroxide ions. So a ratio closer to a 1-to-1 ratio. But the fact that there are more hydrogen ions than hydroxide ions still indicates that it would have a pH less than 7. It would be acidic. Alright, on to question 4, and we've got another example of a situation where knowing your word equations and being able to write symbol equations and then balance them is a real advantage in this paper. So we've got sodium hydroxide and it's reacting with sulfuric acid. So this is a neutralization reaction, an acid plus an alkali, and we need the formulas of each of those chemicals. But before we write the formulas, we'll just write the word equation: sulfuric acid plus sodium hydroxide, an arrow to the products, which are sodium sulfate and water. We would know that it's sodium sulfate because we take the metal from the alkali, so sodium, and sulfuric acid will always produce a sulfate. And again, I told you to memorize the formulas of the acids, the common acids, so hydrochloric acid, nitric acid and sulfuric acid. You should also memorize the names of the salts that they create. So hydrochloric would produce a chloride, nitric acid would produce a nitrate, and sulfuric acid would produce a sulfate salt. So sodium sulfate is the salt in this case. And then the hydrogen from the acid and the hydroxide from the alkali combine to create water, assuming there's that we're dealing with a balanced situation there. So the formula for sodium hydroxide, we write down the ions, sodium and the hydroxide ion, bracket the OH, swap and drop. Because it's a 1-to-1 ratio, we can remove the numbers and we can remove the brackets, giving us NaOH. That's probably one that you'll be familiar with already. And sodium sulfate, we need the formula for that as well. So again, write down using the table of ions the symbols with their charges, bracket the sulfate, SO4, leave the charge on the outside because you're going to swap and drop that, and then that gives us Na2 brackets SO4. Because there's no number outside of the brackets or on the right hand side of the brackets, we can eliminate the brackets, giving us Na2SO4. Okay, so we can write those formulas in place of the word equation to give us the symbol equation, and then we just need to balance it. So again, I'm going to work from left to right, counting up the number of each type of atom or ion on each side. So I've got hydrogen, I've got 2 plus 1 from the sodium hydroxide on the left, so that's 3 hydrogens, and I've got 2 on the right hand side, so there's a bit of a problem there. What I'm going to do in that situation then is I'm going to need to get another hydrogen on the left hand side and double up the number of waters on the right hand side in order to get a nice balance there. And we should be able to reinforce that before I put the numbers in by checking further along. Sulfur, I've got 1 on the reactants, I've got 1 on the products, so that's okay. Oxygens, I've got 4 plus 1 on the left, and then I've got 4 plus 1 on the right. Okay, so that seems balanced. Then I've got 1 sodium on the left, but 2 sodiums on the right, and that's a big clue as to what I'm going to have to do. So I need another sodium on the left-hand side. And the only real way I can do that is to double up the number of sodium hydroxide molecules in the reactants. So I'm going to put a 2 in front of that molecule. Let's see how that looks now. So going back to hydrogens, I've got 2 plus 2 on the left. I've got 4 hydrogens now, and I've only got 2 on the right hand side on the products. So I need to double up my number of molecules of water, and then if I check that through again, I'll see that everything is balanced. For question 4B and C, I've decided to answer both of these points together. So describe how the indicator color changes as sulfuric acid is added to the beaker, and explain what this tells you about the changing pH of the solution. And then explain the relationship between the changing pH of the solution and the ions in the solution as the sulfuric acid is added to the beaker. So again, we're looking at the particular ions in the solution and the ratio of them. Okay, so how does the indicator change color as sulfuric acid is added to the beaker? Well, because we started with the sodium hydroxide, I think it said 5 drops in the previous part of the question. So the indicator color, once we've added the universal indicator, but before we've added the sulfuric acid, the beaker would contain blue once that universal indicator has been added. So that's represents the pH of the sodium hydroxide, a pH of around about 8 to 11. If it's highly alkaline, then it might be purple, which would represent about pH of 12 to 14. And regardless of what the pH is there, as long as it's above 7, then there are more hydroxide ions in the solution than hydrogen ions. As we add sulfuric acid to the beaker, then what we're doing there is we are adding more hydrogen ions, so the ratio between the hydrogen and hydroxide is becoming closer and closer and closer to an equal number of hydrogen ions to hydroxide ions. Eventually, we might reach a point where we've had neutralization, and that would be a pH of 7. If we were to add more sulfuric acid past that point, then we would have more hydrogen ions than hydroxide ions, which would reduce the pH below 7, and the indicator color would go through from green, yellow, orange, and red. And no matter how much sulfuric acid you add after the indicators turned red, you're still going to have a red color to the contents of the beaker. And once the pH has dropped below 7, then you've exceeded the number of hydroxide ions with hydrogen ions. So there's more hydrogen ions than hydroxide ions once the pH is less than 7. Okay.